Now that we have the idea of linear dependence and independence at our disposal, let's return to the question of span. So remember, the whole point of defining linear independence, what we were trying to capture was the idea that sometimes for a span you need all of the vectors, and sometimes you don't need all of the vectors to get the same span. So let's check if linear independence and dependence really captures that idea. So let's suppose we have a collection of vectors that's linearly independent, and let's compare the span of those vectors to the span of all of those vectors except one. So here it looks, I've left off just the very last vector, v sub k, but since these vectors are sort of anonymous, they aren't actual vectors with actual numbers in them, if we rearranged things, we could actually, by leaving off the last one, we could actually be leaving off any of the vectors. So it looks like I'm only using the last one, but really this could be any vector that we're leaving off here. So this first collection of vectors, it's a span, so it's just all linear combinations of all the v's. So from v1 up through vk. And all of the a's, all of the a sub I have to be real numbers. And we're comparing that to this second span, which I'd better not use a's, let's use b's instead. So b1, v1, up through, and then we're leaving out the last one, so we're only going up to b sub k minus 1 times v sub k minus 1. And here all of the b's are real numbers. Okay, so when I say compare, what we need to do is check, is it the case that every vector in the set on the right is also in the, sorry, I did that backwards. Is it the case that every vector in the set on the left is also in the set on the right? So let's suppose that it is. So let's just suppose that we have, for everything in the set on the left, it's possible to write it as an element on the right. So b1, v1, up through b sub k minus 1, v sub, I wrote my b's and k's backwards, b sub k minus 1, v sub k minus 1. So what we're checking is, can we get every vector in the whole span just using fewer vectors? Okay, so we're supposing that we can. So suppose that this is possible. Suppose. Okay. Well, if this is possible, we can now rearrange this equation. So we could take all of these terms and move them to the left. So that would give us a sub 1, v sub 1, plus dot dot dot, up to a sub k, v sub k, minus b sub 1, v sub 1, minus dot dot dot, all the way down to minus b sub k minus 1, b sub k minus 1, equals the 0 vector, right? There's nothing left on the right-hand side, so it's the 0 vector. But, you know, these terms that have the same vector, we can combine these. So this is a1 minus b1 times v1 plus, so all the way down to, let's see, there's a v sub k minus 1 term here. There's also a v sub k minus 1 term hiding in my dot 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 right there. So that's a sub k minus 1 minus b sub k minus 1 times v sub k minus 1. But then there's one sort of leftover term here, which is this v sub k term. So plus a sub k v sub k equals the 0 vector. Okay, well, this might look familiar. This looks a lot like the equation that defines linear dependence and independence. So what we found here is a solution to this equation. So if every vector in the left is also in the right, then we get solution to this equation. The question is it possible that is it possible to get a non-trivial equation? Well, you know, we could choose all the a's and the b's to be, so a1 equal to b1, a2 equal to b2, and so on, all the way up to a sub k minus 1 equal to b sub k minus 1. But right, we could choose any vector out of this collection. In particular, we could choose the vector where a sub k is 1. And what this gives us is a non-trivial solution. Right, what this gives us, so now, right, because we made all of these choices, this is 0, all of these are 0, except for this one right here. Right? So this gives us v sub k equals 0. But we said at the very beginning that the v sub k, all the v's, are linearly independent. But what we just did is we came up with a non-trivial solution, but there can't be any non-trivial solutions to this equation because the v's are linearly independent. So this whole thing is a big contradiction, right? We made an assumption, suppose this is possible, we derived a contradiction. So that means the assumption that we made has to be false. So in fact, it's not possible to write every vector on the left as a vector on the right. Well, clearly, because there are more spanning vectors here, clearly the span on the right is contained in the one on the left, but it's not equal. We just showed that it can't be equal. Not every vector in this left-hand span is a linear combination of vectors in the right-hand span. So what this is telling us is that if we have linearly independent vectors, to get the full span, you really do need every one of those vectors. And that's exactly why we made the definition of linear independence. What this is telling us is that we made a good definition. Our definition really captures the idea that we were after. There's a little more ground we can gain from our definition of linear independence. So suppose that we have some linearly independent vectors, v1 through vk, and we take some vector in their span. So let's ask, how is it possible to write v? Well, we know that v, since it's in the span of v1 through vk, it is possible to write v as a linear combination of v1 through vk, like this. Okay. So there's at least one way to do this, but what we've seen is sometimes there's more than one way to express a vector as a linear combination of other vectors. So what if there's another way to do this? So what if there's another way? Maybe we could write v as with different coefficients, say b1 v1 up through bk vk. What would this mean? Well, let's see. We have these two different ways of writing v, but both of these are supposed to be equal to v, but that means they're equal to each other. So that would give us a1 v1 through ak vk equal to b1 v1 plus dot 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 up to bk vk. But now that we have this equation, we can do algebra on this. We can rearrange this. In fact, we can do kind of like what we did before. We can move all of these to the left and then pair up terms that have the same vector and factor out that vector. So that gives us a1 minus b1 v1 all the way down to ak minus bk times vk equals 0, the 0 vector. But remember, all the v's, we're assuming that the v's are linearly independent. So that means the only solution to this equation is the trivial solution. And the trivial solution is when each of these coefficients is 0. So that means a1 minus b1 is 0, and a2 minus b2 is 0, and so on, all the way down to a sub k minus b sub k equals 0. But right, each of these, we can move the b's back to the other side. We get a1 equals b1 down to a sub k equals b sub k. So what we found here is that, right, we assumed we had these two different ways of writing v as a linear combination of v1 through vk, right? We assumed we could do it in these two different ways, but what we found here is that because the v's are linearly independent, these two different ways are actually the same way. So what we've shown is if these vectors are linearly independent, then every vector in the span of v1 through vk is a linear combination of v1 through vk. So this, so far we haven't said anything new. We've just repeated the definition of span. But the new piece here is that it's a linear combination of v1 through vk in a unique way. So this is the new part. Right? This is what we just showed. So if you write v is, right, some combination of v1 through vk, if the v1 through vk are linearly independent, this is the only way to write v as a linear combination of v1 through vk. And you can see that knowing that this representation, this linear combination, is unique is much better than just knowing that there's some linear combination. And the linear independence of v1 through vk really is playing a key role here, right? In our proof that there is a unique way to write v as a linear combination of v1 through vk, we used linear independence right here. It sort of let us split this one vector equation into many different scalar equations, right? So linear, that's usually the role of linear independence. It lets you split a big vector equation into many scalar equations, and then you can work with the scalar equations independently without having to worry about some sort of weird interaction between the different terms in the vector equation.